Well, hello everyone, and welcome to today's webinar, Artificial Intelligence for Catalysis, presented by the Chemical Catalysis for Bioenergy Consortium, or ChemCatBio. I'm Eric Ringel, the Communications Representative for the consortium, and before I introduce our speaker today, I'd like to just cover a few housekeeping items so you know how to participate and learn more about the consortium. ChemCatBio has several resources available on our website, chemcatbio.org. You can find tools and capabilities, publications, webinar recordings, interactive technology briefs, and a lot more. We regularly update this site, so be sure to bookmark it and keep an eye on the news section on the homepage for notices on ChemCatBio sponsored events and opportunities like this one today. You can also navigate to our tools from the website, including the Catalyst Property Database and CatCost. Another great way to get updates from the consortium is through the ChemCatBio newsletter called The Accelerator. Subscribe to this resource to learn more about ChemCatBio events, funding opportunities, publications, new technologies, and research projects, research teams, and more. A little bit on participating in the event today. You will be in listen-only mode during this webinar. You can select audio connection options to listen to your computer audio or dial in through your phone. You may submit questions to our panelists today using the Q&A panel. If you are currently in full screen view, click the question mark icon located on the floating toolbar at the lower right side of your screen. If you're in split screen mode, that Q&A panel is already open and is located at the lower right side of your screen. To submit your question, simply select all panelists in that Q&A drop-down menu, type in your question, and press enter on your keyboard. You may send in those questions at any time during the presentation, and we will collect these, and if we have time, address them during the Q&A session at the end today. All right, now if you have technical difficulties or you just need help during today's session, I want to direct your attention to the chat section. This chat section is different from the Q&A panel I just talked about, and it appears as a comment bubble in your control panel. Your questions or comments in that chat section only come to me, so please be sure to use that Q&A panel for content questions for our panelists. All right, automated closed captioning is available for the event today. To turn it on, select Show Closed Captions at the lower left side of your screen. And we are also recording this webinar. We will post it on the ChemCatBio website in the coming weeks, along with these slides. And please see the URL on the screen here for where to access that. I'll put it in the chat here in a second as well. All right, lastly, just a quick disclaimer I need to read. This webinar, including all audio and images of participants and presentation materials, may be recorded, saved, edited, distributed, used internally, posted on the U.S. Department of Energy's website, or otherwise made publicly available. If you continue to access this webinar and provide such audio or image content, you consent to such use by or on behalf of DOE and the government for government purposes, and acknowledge you will not inspect or approve or be compensated for such use. Okay, our speaker today is Rajeev Assary. Assary is a computational chemist and group leader at the Materials Science Division of Argonne National Laboratory. He is also the Argonne Principal Investigator of the U.S. Department of Energy's Consortium for Computational Physics and Chemistry, or CCPC for short. Rajeev's interests include AI for materials chemistry, decarbonization, and digital discovery for energy storage and conversion. Rajeev has published over 200 peer-reviewed manuscripts and proceedings. And as another quick means of introductions, I'd like to start us off with a short video, and then we will dive right into the presentation.
I am a computational researcher. I use supercomputers to do computations that can enable catalysis or chemical reactivity at surfaces. Similarly, I use power of data science techniques to come up with the connections we can make to predict new catalysts or better conditions for catalysis. Yeah, this is an awesome opportunity to connect with the various aspects of catalysis, from discovery to all the way to deployment. So the computations, as an enabling technology, it can tune into various aspects of this research. So that is one of the reasons I'm part of the ChemCatBio community from the day one. We have a very good working relationship. If we don't know certain things, we will reach out immediately so that we can accelerate our learning much effectively, basically.
All right, Rajeev, the floor is yours.
Okay. Good morning, good afternoon to everyone. Thank you, Eric, for the kind introduction and organizing this ChemCatBio webinar. First of all, it's a great pleasure to present, contribute something to the ChemCatBio webinar as a decade-long CCPC, a member of this research ecosystem. So today's webinar is all about AI for catalysis. First of all, I am a group leader at Material Science Division at Argonne. My major research interests are energy storage and chemical catalysis and decarbonization. The various tools such as AI for materials, autonomous material discovery, these are used in moving towards clean energy and sustainability. So these three topics are some strategic importance to Argonne National Lab, and I'm happy to be involved with this. So ideally, what we need is utilize this power of AI and high throughput experimentation and this robotic experimentations to make discovery of tomorrow's materials much faster, so that we can achieve decarbonization and clean energy and sustainable economy. So let me start with a catalysis dream. Imagine if dream. If we could design, discover, and demonstrate, deploy optimal catalysts faster and cheaper with the help of AI. I think that's the real promise of AI at the moment. So if you look at the bottom of the slide, you can see an optimal catalyst, which is this is something what really decided based on multiple optimal properties. For example, cost has to be cheap, operating cost has to be cheap, and it has to, catalyst has a optimal selectivity or high selectivity and stability and recyclability and all of those objectives. So we want to make sure that we maximize all these positive objectives using all the available tools at the moment. For example, literature, limited experiments, analysis, modeling, and the AI tools. I think the great aspect, great opportunity for AI is AI can help analyzing all these things, and hopefully AI can help us moving to design and discover new effective catalysts. So now, what are these AI tools? I mean, if you look at the slide at the bottom, I mentioned about AI. AI is about creating intelligent agents that can reason, learn, and act autonomously. Most importantly, it has to exceed or match a human intelligence. So we know that human intelligence is a subjective question, same as artificial itself a subjective question. So almost all the tools we developed over the last couple of decades can be coupled into or a part of a subset of this AI. For example, machine learning, where we use algorithms to understand the data or classify the data or predict certain property. Simple example is image classification. We can classify images in multiple buckets. Similarly, we can predict, let's say, cost of a material or cost of a product. A step up to this machine learning is a deep learning. It's also a subset of machine learning, but it has been developed much faster, and it's highly parallel mechanism for understanding complex patterns of the data, utilizing deep neural networks. The principles we can it's highly parallel, and it is a GPU or a graph programming unit compatible. So quite a lot of recent developments all happened in the deep learning era of image recognition and natural language processing, etc. The top two are recent developments. GM means generative models, and LM indicates language models. So language models is the a recent trend of machine learning world. It's utilizing our predictive capability of, for example, text prediction based on contextual learning of what's happened in the entire universe. So it has access to almost all the World Wide Web information and many publications and reports. So these the generalized generative models and large language models also I will mention towards the end of the presentation. But majority of the scientists at the moment working in the interface between machine learning and deep learning to understand their data. So how can we use this AI and computations together to make some solid contributions to Catalysis? So I just want to point out, I'm a computational model, so my catalysts are much more beautiful. If you look at the right side, this is a beautiful catalyst. The surface of in this case is a molybdenum carbide catalyst. So three type of activities of computations of AI can help the ecosystem, Catalysis ecosystem. One is AI guided design. So it is two type of approaches you can use. You can use an informatics based approach, collect all the data or all possible information regarding the catalysis. It's a library of fundamental science. And also, if you know the existing catalyst regions or existing catalyst materials and conditions, we may be able to help to optimize these conditions. So AI guided designs is mainly used in this the discovery and design and optimizations. The bottom two lines are a little bit more tricky. For example, creating new materials. For example, two processes there is automated chemical synthesis, that's synthesis of a catalyst using robotics, and also automating or AI-enabled materials characterization. These two areas are emerging areas. I think we need quite a lot of developments in robotics and also data management to make more progress. In the final part, I think this is the world is going such a way that we need to access all the public accessible information regarding the catalyst, and also it has to be verifiable and also has to be accurate. Otherwise, we are modeling completely based on completely wrong information. So catalyst knowledge accessible for everyone has to be one of our prime concern, and this has to be included. The accurate information has to be included as part of a next generation, foundational models, etc. So one slide about AI for material science in general. If you look at on the left hand side, I think this is the larger umbrella of AI and machine learning and deep learning. So if you look at it, machine learning, it's commonly used techniques because computationally you only require 100 or more data points. You can start making the power of certain algorithms available. For example, naive Bayes or random forest or Gaussian process regression. So these are all computationally less intensive because they have a closed for mathematical solution. So you don't need a supercomputer to run for any of this, provided you have a decent data, good data. Deep learning, you mentioned, there is quite a lot of development happening in deep learning. We always require more than 500 or 1,000. In my experience, many times you need 10,000 or 50,000 data points, high fidelity data points to make a meaningful prediction, but it can understand any complexity using, let's say, a simple function. It can optimize or understand any function as a solution. For example, the input of your model can be just a text or let's say a descriptor matrix. It's a tensor, or even an image or a videos or a combination of all of this. It's a multi-modality. I think this deep learning has developed into that point. On the right-hand side, I have shown a picture from a paper published by Meta and Carnegie Mellon University. I think it's called Open Catalysis Catalyst Project. So this is probably the largest data set available for Catalyst, for catalysis in terms of atomistic modeling. So this is around more than 1 million DFT calculations. It's still limited to simple oxides, unary oxides and binary oxides, and also it's limited to hydrogen evolution reactions and oxygen evolution reactions. Nevertheless, this is kind of one of the best models out there, and they don't have any kinetics information. So one more slide about the ecosystem associated with these materials. For example, quite a lot of development happened in the last couple of years. This is showing a bunch of examples. ChemCatBio itself have a data hub, can provide quite a lot of DFT information. Similarly, Materials Project, it is a database for solid state materials, and the materials data facility is another example. So the slide meant to show that the community has started making some targeted data generation, so that we are all getting some benefits for utilizing this data to develop machine learning models and some sort of predictive design. So just this also meant to show AI for catalysis is extremely growing area. If you look at any flagship catalysis journals like ACS Catalysis or Green Chemistry, the amount of AI papers coming out for predicting some sort of catalyst conditions or a catalyst active site, or exploring the complexity of reaction networks, or accelerating the kinetic predictions are enormous. And we have plenty of opportunities to grow. For example, if you look at the general AI papers are in the 10 to the power 4, this is the relative intensity. I think now LLM, for example, large language models are creeping up because everyone likes this promise of large language models. AI for material science and material informatics, they are teeny fractions at the moment, but quite a lot of discovery requires some information. So I think this histogram, the bar will definitely going to grow up. So let's recap. Now we have a lot of tools available for catalyst design. If you are a computational chemist like me, I think this is an exciting period of time. So I grouped these tools as 6 categories. So first 2 of them are expensive. For example, first one, my favorite tools is physics-based simulations, DFT and molecular dynamics simulations, so that you can look at the catalyst active site and possible chemical reactions at a very small length and time scale, but reasonably accurately. So to extend this kind of a time scale and length scale, you can make statistical models or a Newtonian dynamics or a Monte Carlo type of simulations. So you can, that is the category number 2. And the 3 is data-driven catalysis. So there we can utilize quite a lot of this data developed in the number 1 and 2 category and the experiments to make reasonable predictions. 4 is on-the-fly approaches. For example, if you are interested in doing on-the-fly understanding of a spectra or a synthesis of materials, we need to make sure we will get a kind of actively learned system, so that we improving the predictions after every iterations. So it's more a self-supervised learning. And 5 and 6 is the latest trend about large language models for example, programs like a ChatGPT or Llama. This kind of information is this will take care of a lot of information from the internet or all the available data. I think this is a place we need verifiable data, and that ChemCatBio and CCPC and all other community can play a vital role in providing very accurate information. So just want to point out quite a lot of exciting work happening in the atomistic scale modeling, mesoscale modeling, and continuum scale modeling at CCPC. And in my own experience over the past 10 years, I think we worked quite a lot of chemistry, from vapor phase chemistry to surface catalysis, ring opening chemistry, reductive etherification, ketonization, etc. So much beautiful chemistry topics happening. So we started applying this. These are all complex chemistry. So the AI and DFT and machine learning started applying to this slowly. So now back to two topics. I am very much interested to tell you the story. This is the two stories. One is about designing molecules. Another is understanding properties of the catalyst. So these two works are published in Digital Discovery last couple of years. I think this both of them are open source journals. I think all the data, all the GitHub information are free to get. So you can download. You don't need any subscription. So let's get the first point. Here I am talking about how to discover a new molecule. So in this case, this molecule is a hydrogen carrier. It's very similar to, let's say, benzene or a cyclohexane. So they can store hydrogen. These molecules can store hydrogen so that you can use a catalyst to take hydrogen from the molecule, which is a dehydrogenation reaction, and you can put the hydrogen back whenever you need, whenever you can, using other catalyst, hydrogenation catalyst. So there is also catalysis is one of the most important steps. But in this point, I'm just talking about. So there are some molecules are already available for storing hydrogen. Simple example is methanol and ammonia. So in this case, we are talking about a completely new type of molecular understanding or a new type of molecule. So the question we asked is there any molecules in the chemical universe that we haven't thought about utilizing as a hydrogen carrier? I think that is the question we asked. So for example, first, so the scale is slightly big, so that's one of the reasons I'm showing this study. So we know that there are some molecules available based on chemical intuition and also studies by organic chemists. For example, Bob Crabtree from Yale has come up with this type of molecule. It's called a liquid organic hydrogen carrier, around 35 molecules or 40 molecules. So if you know any of these molecules, so what first thing we can look at it, is there any molecule look alike them, has similar properties? I think that is the concept we took here. So we looked at one data set, precisely I just want to tell about GDB17, which is 17 heavy atoms. So we identified a data set from literature. It's called GDB17, which is around 166 billion molecules. So we used this similarity criteria. In this context, the criteria is called a Tanimoto similarity. It's about looking at how these molecules are similar with respect to this 35 or molecules that we know. So when you look at this large number, 166 billion, not everyone can do it. I think this is one of the reason we utilized the power of supercomputers. So in this case, we looked at the 166 billion molecules, around 8,000 nodes of supercomputer, around 3 million molecules per second. So we identified that there is around 1 million molecules have a highest amount of similarity with our test set or the realistic molecules available from the chemistry studies. So from that also we have 1 million itself a lot of molecules to recommend to an experimentalist. So we thought about we deduce it further using some scoring criteria. The development of the scoring criteria is also a chemistry involved process. You need to understand how the molecules looks like, and so there are some rules we utilized. to understand, utilize for heuristic screening. So the details of scoring criteria is in the publication. Further, what we have done is we have utilized a DFT-based approach. For example, in this molecule, if you want to check hydrogen out and put hydrogen back in, it has to be reasonably easy, within 40 to 70 kilojoules. So with that information, and also we looked at these molecules are whether they have a melting point and boiling point matches to liquid organic hydrogen carriers. So we used a practicality screener around 37 new molecules from this one. I think the data set is available in the GitHub, but a couple of the examples shown here. These molecules were reported not as liquid organic hydrogen carrier, but the story is not finished. I think this is we are continually looking at opportunities for doing the experiments, real experiments, which is most likely with the difficult steps for this process. And also, as I mentioned earlier, we have these areas of liquid organic hydrogen carriers is getting a lot of attention. Part of maybe there is an opportunity for a mixture of hydrogen, liquid organic hydrogen carriers. So there is a need of more data. One of our coworker, Hassan Harb, is already developed a 10,000 accurate energetics of these materials, 10,000 of this new molecule. I think hopefully that can be also help us to develop further information regarding this system, and also we are interested in developing some sort of a kinetics index for this. So this is that was a complicated paper. I think one of our co-workers from Argonne, Joe Harman, he wrote a very nice taxpayer description of these highlights. I think majority of the group members started understanding much more about this project after reading this nice description. Let me get back to the catalysis problem here. In my talk, I think here to switch suddenly from molecules to catalyst. So this is a completely developed as part of our ChemCatBio and the CCPC. So one of the principal objective is how to develop active and inexpensive deoxygenation catalysts. We know that majority of you guys know already. Removing oxygen is one of the most difficult process in the catalyst in the catalysis of biomass. So to get this, I think we started looking at an exemplar problem. In this case, is removing oxygen from bio-oxygenates and the bio-oil. So we utilized a catalyst of a molycarbide. One of the reasons is majority of the best catalysts are platinum and alumina or platinum or some other oxides. These are expensive. So if it's a molycarbide type of catalyst, they are reasonably cheaper, but they all typically almost all catalysts, all the transition metal catalysts has a tendency of oxidation, which is thermodynamically inevitable. So bottom there is a couple of publications. This catalyst can be used even also for CO2 reduction. So the question is, when you have a catalyst, when you remove oxygen, they bind on the surface of the catalyst. So so now we have not only just a catalyst, but it's an oxygenated catalyst. But now, if you want to regenerate the catalyst, you need to remove the oxygen by extra feeding hydrogens. So, for example, oxygen can be removed as a hydroxides, and hydroxides combine each other to water to remove water. So if you can see that oxygen binding is strong, it's not secret, it's strong. So it's very difficult to remove the oxygen as a water. But if you decorate the surface with something like a nickel, the removal is a little bit more easier. So this is something we want, because we want to regenerate the catalyst a little bit more easier. I think this is a very clean facets, and calculations done in molycarbide 100 facets. It's a very clean chemistry here. So now we ask the question: can we design a moly-carbide catalyst or something like this to facilitate oxygen removal much faster with a reasonable stability? So the key message here is oxygen binding can be used as a descriptor. So in future, if you can predict the oxygen binding of a catalyst, it is much more desirable to predict this oxygen binding of this catalyst, and this can be helpful for a Wolf construction of a real catalyst and understanding local reactivity. But there is not much data available, and also in this kind of systems, we are only looking at oxygen binding as a descriptor. It's very simple systems. So we decided as part of CCPC, we developed this catalyst data using in silico approaches. For example, in this case, we looked at moly-carbide with their 7 lower Miller indices and almost all possible type of termination. It's around 54 type of terminations, and we doped the surfaces with almost 23 dopants from the periodic table. So we come up around 20,000 catalyst structures. 20,000 catalyst structures, and we have 20,000 catalyst structures, and then we include the binding energies of oxygen, which is oxygen can bind pretty much a lot of places. I think there are sophisticated tools like a CAD-KIT and ASC kind of computational tools can be used to develop this stuff. So the long story short is 20,000 calculations or 40,000 calculations cost around 15 million CPU hours. I think we got through ALCC allocation at Argonne. I remember I think Trevor and Jeremy were very supportive of this one to get this allocation. So utilizing this data, now we have a catalyst and we have binding energies. Utilizing this data, we develop a graph neural network. So in the future, we don't have to do DFT calculations. We can just to show a graph of the structure, graph of the catalyst or local site, you can predict the energy. So this approach is called a local coordination graph neural network. So now we have let's say on the left side there's a histogram that's showing 20,000 binding energies of oxygen on this catalyst. On the middle, we utilize this graph to predict the binding energy and compared with the computed binding energy, because we already have the truth value. So while we published this data, I think the mean absolute error was 0.18 EV. That means if you just show a graph structure, it will predict the binding energy with a reasonable set of accuracy. I think now we have even reduced this significantly lower because of the help from computational folks. So on the extreme right hand side, you can see that around 15K data set is needed to even predict this one. And these are quite good numbers, because moly-carbide is not like a simple palladium catalyst or platinum palladium oxide catalyst. So this is a little bit more complicated catalyst. So we are very happy that we got a decent value while we published the data. One more quick example of power of these deep neural networks. If you look at it on the extreme right hand side, if you take out a machine learning model and do a gradients of the final output, you will get a norm gradient or saliency map. So if you carefully see it, the saliency map higher and lower, it indicates oxygen binding is less and weak. For example, tantalum, we know that tantalum is a higher Lewis acid than cobalt or nickel. They can bind, they bind the oxygen very strongly. So, and also from a T-SNAP plot, we can also see the binding energy is also associated with this coordination number of coordination with the oxygen. So it is taking care of almost the machine learning model is taking care of almost all the physical constraints or molecular knowledge we are providing. So this is a good opportunity to utilize this machine learning for probably in future for a Wolf construction kind of stuff. Similarly, I think Joe also wrote a nice article about this one. the beauty of this one, you can predict this oxygen binding in milliseconds compared to 5 hours of periodic DFT calculations. I think that is the beauty, and hopefully we will be utilizing this for this model for other binding of let's say carbon and oxygen for CO2 utilization as well as water formation. So in the last 2 slides, I think I just want to quickly mention about recently there is a huge interest in natural language processing and this large language models. I think this is one interesting quote I saw. LLM can do jaw-dropping things, and but nobody knows exactly why. It's from a technology review in MIT. This is true. I think we in the community, I think there is a lot of information out there. Some of them are useful, and some of them are not really useful. And on the right-hand side, you can see quite a lot of large language models now, and autonomous agents are now leveraging chemistry and materials knowledge. It's quite a lot of them. I think this area is growing so rapidly at the moment. So we need to utilize this kind of tools for a catalyst design or process design in the coming age. For example, there are ways you can do it now. We can look at some any of this, let's say CatILM, which is a latest electrocatalysis large language models released from China. This kind of large language models, you can take it and you can retrain them or fine-tune them based on some existing catalyst data which you trust a lot, so that it can take care of what is happening the outside world and whatever the data system you have. And also you can provide quite a lot of your domain knowledge from publications that you have and you collected over the period of many years as a PDF document, and you can convert this to some sort of a RAG model, which is called a retrieval of augmented generation models, to generate more new chemistry. So soon, I think for sure, I think now Siri is also want to work on OpenAI. So soon you may be able to ask Siri for a catalyst recommendations. I think the text on the right it's a bunch of possible outcomes you get from Siri, but verifying these things require quite a lot of domain knowledge. So this won't take away anybody's job, but it will create you, it will give you a large amount of tools so that you will be able to utilize for your discovery, catalyst discovery. I think that's all I have. And in summarizing this one, I think in a high level, I showed molecular discovery is possible with from an extremely large chemical space if you can combine with the atomistic modeling, and also data-driven material property prediction. It depends on the data, and near term, this binding energies and the microkinetic modeling can be solved for a given catalyst in terms of designing the catalyst. I think the experimental synthesis of a catalyst and or measurement or verifying the kinetics is going to be crucial. Similarly, the red hot topics is there is a vast opportunity for us in community to use the growing strength of AI, especially the large language models and deep learning. I showed the examples, and we can develop a huge data sets with a dedicated data generation efforts. So as I mentioned, there is a huge opportunity for AI for synthesis of catalysts as well as characterization for catalysts. With that, I thank you, CCPC and ChemCatBio folks, and I'm happy to answer your questions. Thank you.
Awesome. Well, thanks, Rajeev. Very interesting and informative presentation. We do have time for a couple of questions. So as a reminder for the attendees today, you can use the Q&A box to submit your question right now. Just type in your question and we will ask it to Rajeev if we have time. And just to kick things off, Rajeev, I'll warm things up with a question here. So what would you say is the role of ChemCatBio in the AI world as you've kind of described it in your presentation today?
Yeah, I think the good thing about ChemCatBio is a huge ecosystem. I think we have both we have modeling, we have experiments and characterizations, synthesis and everything. So a topic, if we are interested in a genuine catalyst area, I think we can provide a significant amount of data sets from the design to testing. So which is the high fidelity data of the catalyst thing, which is not easy for let's say university. So because we can provide we can cover large aspects of this catalyst discovery process.
Great. And then a question about catalyst characterization. Is there a role of artificial intelligence in doing that kind of work?
Yes, I think so. Catalyst characterization often is a complex process. I think the signals are complex, so you need some sort of a data reduction techniques. So the AI can definitely help. I think, and there is a huge value for it because we need to understand what is happening on the catalyst surface very clearly, so that we know what is the desired outcome of the catalysis process. So the imaging techniques and multi-scale modeling can really help. So the AI of this area is slowly emerging. I think this is the time we should invest more time and efforts to for characterization.
Okay, I have another question that just came in. So how do large language models convert graphs and pictures if only the catalyst data is available from literature or just image data? If you need me to repeat any of that.
No, I understand. I think all of the above. Large language models can take care of text or tables or images and get the information. This is a large language models generally good at learning the context or make connections from one another. So if you show many of these images and many of this context, for example, moly carbide has this spectrum and vanadium carbide has another spectrum. So they start understanding the relationship between these the images as well as and the text and the tables and everything. So it requires a little bit more fine tuning because of these are not necessarily completely available in the open data sets, open literature. So we may have to fine tune a little bit for our specific task. So that area is autonomous agents. It's actively flourishing at the moment.
Yeah, thanks for that. Couple more questions came in. Is ChemCatBio or ElectroCat or CCPC interested in developing a LLM or GPT or agent model?
Well, yeah, developing any models is not easy task. It requires quite a lot of. I mean, we are talking about millions, tens of hundreds of millions of GPU times and manual times. So we may not develop anything. Most likely, we will gather information on the catalyst of interest and probably use a fine tuning approaches. So it requires significant investments.
All right, I think we have time for maybe just one more, Rajeev, and this is a little bit of a longer one, so I'm just going to read it here. Since the atomic scale models can calculate efficiency and performance based on specific atomic structure and catalyst atom location, can these tools be used to, one, predict performance from a mixture of catalyst structures, and two, show potential synergistic roles for such mixtures? If you need me to repeat any of that.
No, I understand. I think this is a very good question. I think atomistic model itself a very simple representation of what's going on in the catalyst. I think to understand how this synergy works on various catalyst sites, I think we probably need to construct a set of model situations when the active sites coexist and chemistry happens between these sites. I think we need a dedicated, some deep dive studies or a descriptive analysis for this stuff, for answering for sure.
All right, well, I mean, I think we're right at the end of our time here. Appreciate all the questions and engagements. And thanks for everyone who just joined us. Rajeev, thank you for sharing your experience and expertise and research here. Just as a reminder to the group, a recording is going to be available on the ChemCatBio website as soon as it's available, probably in a couple of weeks or so. If you have questions in the meantime, we encourage you to contact ChemCatBio through our website, chemcatbio.org, or you can email Rajeev. You can see his email on the slide here. And then while I have you, I'll make one last plug for the ChemCatBio newsletter called The Accelerator. I'm going to put a link in the chat. This is a great resource to keep tabs on further updates or other events like this one from the consortium. So with that, I think we will take our leave. Have a great rest of your day, and remember to stay tuned for future ChemCatBio webinars. Thank you.
Thank you.